a really important concept that I completely forgot about. There's just so much to go over. I don't know what I'm going to do with myself, but one thing I noticed is the equations of state for stellar structure, meaning the state the star is in, contain no coefficients for thermal contraction or expansion. The reason why that is because establishment has stars as being static structures inside of their equations, and then they just threw in the towel. They weren't interested in what's called volumetric thermal expansion and contraction during stellar evolution. But that's very problematic, because if you have no thermal contraction or expansion equations, then you're basically not even looking at the star as it loses heat or gains heat. As a general rule of thumb, there are different substances which don't obey this general rule of thumb, but as a general rule of thumb, thermal expansion of gases, liquids, and solids means that those materials absorb heat, which means it's endothermic. And as the material absorbs heat, it gets bigger and bigger and bigger as the molecules gain kinetic energy and they bounce off each other more rapidly. And as another general rule of thumb, as an object is large and it releases heat, thermal contraction takes over of gases, liquids, and solids, meaning the material contracts. It gets smaller and smaller and smaller. And that would be an exothermic reaction. Now, when you reference stars, the entire thing doesn't obey this, given the star doesn't lose mass. It obeys this as the star loses mass as well. So not only is the star going to shrink because it loses mass to solar radiation, solar flaring, and coronal mass ejections, but that it gets smaller because of thermal contraction. The star cools down, and it also gets smaller from plasma recombination. Meaning there are a whole bunch of different ways the star contracts and gets smaller and loses mass as it evolves. And it's very, very complex. But if there are any math people out there, factor in a coefficient for thermal contraction of aluminum, or hydrogen, or helium, or oxygen, or nitrogen, and apply that to the star as it evolves and see what happens. Now, the reason why I wanted to go over this is because a lot of people, they don't quite get it, so I'm just going to share this with them. But if a star is really big and hot, and it loses energy to its environment, and basically enthalpy, the amount of disorder increases, obviously, but it also loses enthalpy, meaning heat. So it's kind of strange how the object becomes more disorderly, but also becomes more orderly as it evolves and differentiates itself. I just thought I'd point that out. At the same time, this would be the sun, this would be an orange star, this would be a red dwarf, this would be a brown dwarf, and this would be like a Jupiter, this would be like a Neptune, and obviously it just keeps on going. But it will reach a point to when all the material is crystalline structure, and the coefficients for thermal contraction or expansion will decrease considerably, which means the amount of heat pumped into or out of the star will not make it change that much more in shape or in size, because there's just no place for the molecules to go. They're already stuck there in a crystalline, amorphous structure, or whatever it is, rocks and minerals. But since the star, when it's really young, it will change a lot more because it's more open to change. The molecules are more free to move around. But as it evolves and releases heat, it contracts, and the molecules get more and more trapped as, you know, the star forms more and more solid material. But there you go. If anybody has any questions or comments, leave them below. And I also suggest looking up volumetric coefficients for different material. I have a little list here that I printed off on Wikipedia, but basically it has a whole bunch of linear coefficients and volumetric coefficients. But keep in mind, when you look at that, you should notice the temperature is at 20 degrees Celsius. So when you look at that, those measurements might be a lot different, given they're going to be applied to a star as it evolves, meaning it's going to be a lot hotter, and there's going to be a lot more pressure as well. So there you go. All right. I'll probably go over more of this in the future because I have a lot more work to do concerning it, but that should sum it up.